Quick show of hands. How many of you think that the answer for this is a real number? No real number. So what's the alternative to it's a real number?
Not real number.
Not a real number. AKA, what's that word we learned? Diverging. Yeah, it's a diverging answer. AKA infinity or negative infinity or something like that. Okay. So let's see what the details look like on this one. This one is a little bit less clear on the idea that it was improper, because all the other ones we looked at, I think, so far, either one or both of those limits were infinity or negative infinity, and so that's like a very obvious improper integral. This one was less obvious. What makes this one so improper?
The second term goes to zero.
The second? I only see one.
If you do the antiderivative and then do
I just forgot.
Oh, okay. I think there's a different reason. Like before you get to the FTC2 thing, before you get to that, I think there would be another way you could identify that this is improper. Or FTC1 maybe. Like what would be the other way?
What other way?
So like what I'm questioning is like how would you even know that this is an improper integral? Because it's not obvious, because the two limits of integration are both real numbers. If either one or both of those was an infinity of some kind, then you'd automatically know it's improper, I better use a limit. Like what prompted you to use a limit as x approaches whatever? There's a vertical asymptote. That's it. The graph of 1 over x cubed. It's got a vertical asymptote. So if you did look at the graph, you'd maybe see something like this where you've got this routine going on, and we're talking about the integral from 0 to 2. And so here is 0 and here is 2. So you got all this lovely area in here, except, well, that's a little bit too large. Except, you see how the area could like sort of leak out the top? That's what makes it improper, right? The graph is never going to hit the y-axis. You've got this vertical asymptote and infinite discontinuity. Therefore, this is an improper integral. And that's really important to know, right? Because right off the bat, it's not obvious that this really is an improper integral. But it is because of the graph. Okay, so once you recognize that, you'd want to put the limit as x approaches 0 from the which direction? You know what? Sorry, it should be a b. Limit as b approaches 0. Any idea on what the directional should be there? It needs to be from a certain direction. It'd have to be from the right. Yep. So limit as b approaches 0 from the right, because we're talking about numbers to the right of 0, right? Like 1/2, 1/4, 1/8, 1/16, that kind of thing. Of the integral from b to 2 of x to the negative 3 dx. So again, if you try to complete something like this and you never put the LIM in there, you've got an issue, right? You've got to use a limit to be able to handle this. Any questions so far?
Why does it have to be from the right and not just the limit? I mean, I guess I understand because there's no line on the left, right?
Well, technically there is. So this one, sometimes it was going to make a big difference. Other times maybe not. This one I think would make a pretty big deal because the graph of 1 over x cubed looks like that. So if you approach 0 from the left, you're going to get a bunch of negative numbers being added into the mix. Whereas if you approach from the right, it's a bunch of positive numbers. So for this case, definitely would matter. Yeah, because you could do the other one too. You could do the other side, like -2 to 0 or something. Good question. Anybody else? All right, so then we find our antiderivative. So that would be the limit as b goes towards 0 from the right. And it would be -1/2 x to the negative 2. Evaluated from b to 2. This is where we plug in. So you'd say limit as b approaches 0 from the right. FTC1 gives me, oh gosh, what is that? -1/8?
Yeah.
So -1/8 minus -1/2 b to the negative 2. So it's really plus in there. All right, so it's -1/8 plus the limit as b goes to 0 from the right of that other part, right? So if you wanted to, you could put it in as -1/8 plus the limit as b goes towards 0 from the right of 1/2 b to the negative 2. The bottom line is, what's the value of this? That's the part that diverges, right? Because isn't this really a denominator? And as b gets closer and closer to 0, the denominator will get smaller and smaller and closer to 0, making the whole fraction get bigger and bigger and bigger, right? So it's basically negative 1/8 plus something diverging. So we would say this is infinity, also known as the integral diverges to a non-real answer. Okay, so all the steps, like the steps need to be there. You can't just like jump to the end and be like, it diverges. If you're asked to show work here. Some elements you got to have. You better have the limit as b goes to 0 from the right. Obviously, you better have your antiderivative, show FTC1. Then from there, if you can evaluate that limit a little quicker than I did, that's fine. There you go.
So on those, like, would you write out your answer? Would you like it to be both infinity or and diverges, or just a diverges, or like, could you say
They're
just
pretty
infinity?
synonymous. I'd say they're synonymous. You could put one or the other. Yeah. We'll start to work towards that language of diverging a little bit more frequently, but I'd take either one. Okay, what else? All right, then, why don't you guys try example 5? If you guys are supposed to find this whole integral from 1 to infinity of f prime of x, isn't this one of the ones where the fact that it's improper is a little bit more obvious? What's the dead giveaway? The infinity, right? It's like obviously improper. And so if you don't use this, you're going to have some issues. Why is it, I think you know the answer to this. Why is it that we had to put a directional on that 0 in the previous example, but I don't have to put a directional on, thank you, Emma, I caught that. Why don't I have to put a directional on my infinity?
Because there's only one side that you can approach it.
Yeah, you can't approach infinity from the other side, from the left. From the, I mean, it's like, right, just count backwards towards infinity and you eventually, no, you can't do that, so there's no need to worry about that. On this one, the only main trick that you got to see here is what's the antiderivative of f prime? It's just f, yeah. So be the limit as b heads towards infinity of f of x evaluated from 1 to b. And then it would be the limit as b heads towards infinity of f of b minus f of 1. Okay, so I think from here, we got what we need, right? Because f of 1 is 5, and limit as b heads towards infinity of f of b would be what? Negative 8, right? Right up here. Why on earth would we get negative 13? Like, what would the graph of f prime have to be like?
Has to equal 5, 1. That's where I start.
I would say it.
But
Like, what does that mean if you accumulate using a definite integral and you get a negative number?
Oh, it's under the x-axis?
It's under the x-axis. So something's decreasing, I agree. F would be decreasing. But f prime would be below the x-axis, right? Okay. Anyways. Questions? You guys getting the hang of this? There's some more levels of challenge left. One of which we are not going to do is example 6. For our friends Jeff and Jaden, we haven't covered how to do that one yet. So we'll come back around to that one later on. But we are all able to handle a question like 7. So if you guys would flip ahead to 7. Can anybody explain why example 7 is even an improper integral?
Is
it's between 4 and 2.
What's between 4 and 2?
Ah.
3. And what's so important about 3?
It's
It is a vertical asymptote.
The vertical asymptote at 3. That's right between 2 and 4. So I want to give you guys a couple minutes to see if you can kind of formulate what to do here. I haven't told you exactly how to handle this yet, but you have a lot of tools you could use. I'll give you a few minutes to try it, and then I'll give you a little bit of a shorter time. I'll make sure you understand, let you finish it, okay? Ready, go. See what you can do with example 7. Off on the right path, and if you need to make a little correction to a path, then let's do that, but I'll let you try to finish it up here too. So if I am not mistaken, I think that this graph looks something like this, the vertical asymptote at 3, and then I think it kind of looks like the volcano routine where it's like that over there and this over here. Do any of you guys graph this on your calculator? I think it looks something like that, doesn't it? Okay, so we're trying to find the area essentially from 2 to 4, and of course you can see that we've got kind of two issues here, right? We're kind of leaking out the top of that one and also leaking out the top of that one. And so is it going to end up being a real number? Is it going to end up being the diverging answer? So here's how you'd set this up. I want to make sure that you would have this set up right. Maybe split up the integral to begin with. So it'd be the integral from 2 to 3 of x minus 3 to the negative 2/3 dx plus the integral from 3 to 4 times x minus 3 to the negative 2/3 dx. Does that make sense? I think you really need to split it up like that. And then we put our limits on here. Limit is b heads towards 3 from the left of integral from 2 to b. And then a similar limit strategy with this other one, except it would be b approaching 3 from the right, integral from b to 4. Any questions on that setup? Oh, it showed up. I don't know, there was a little lag there. Okay, questions? So maybe you needed to make a little course correction there, maybe you didn't. In either case, let's see if you can reach a conclusion as to what this ends up being. Is it going to diverge? Is it going to be a real number? We're dying to find out. Let's find it. So hopefully you recognize this pretty straightforward chain rule. Timmy didn't mess it up. It is a flip up. So we'd go limit as b approaches 3 from the left, and it would be 3 times x minus 3 to the 1/3. Evaluator from 2 to b plus the same kind of looking thing over here, approaching 3 from the right, also of the exact same integrand, this time evaluator from b to 4. You see how there's just a lot of details you got to keep track of here? A lot of precision for sure. Can't be super sloppy and expect to do okay. All right, so then we come back over here, and I'm going to do my FTC1. So limit as x approaches 3 from the left. Should start to take shape. It's going to be 3 times b minus 3 to the 1/3 minus 3 times 2 minus 3 to the 1/3 plus, let's put this on a different line, limit as b approaches 3 from the right of the exact same sort of thing, except a 4 is there, and the b is now over here. So again, there's your FTC1. We're ready to evaluate the limits. So what happens with both the expressions where the limit actually has some context? They both go to 0, right? So like this here would go to 0, and this here would go to 0. And so then we're simply, wrong one. This goes to 0, and this goes to 0. All right, so then that actually makes this a lot easier, doesn't it? So up here, 2 minus 3 is -1. What's -1 to the 1/3? That's right, times -3 is just a 3. Plus, well, the other one, of course, 4 minus 3 is 1. 1 to the 1/3 is 1 times 3 is 3. I got the monumentally difficult 3 plus 3 to finish this. Do you guys get 33 like me?
How many is
Do some-
23?
Let's do some.
Ah, we're so close.
How many is
Man, this is the hard part for me.
Four.
It can be. I know.
For me.
It definitely can be.
I was like,
So
when you say a
6.
number,
How'd that go?
say how
You guys did a lot of that on your own. Maybe you worked with a friend or whatever, but a lot of that was done without any of my help. Do you have any questions?
Just keep forgetting the limit directions.
So I do have kind of an interesting, what I think is interesting question to pose to you. Would you guys agree with me that example 7, like when you think about the graph of example 7, wasn't that pretty similar to the graph for example 4? Let me remind you, example 4 looked like this, and it was the integral from 0 to 2, right? So we were looking at this, that area right there. So do you see how that's really similar to being 1/2 of the graph we just looked at? In fact, I know in previous years we've done this example, and people have asked this. They've said, hey, I noticed that this graph for number 7 has a degree of symmetry to it, doesn't it? Isn't the graph symmetrical about the vertical asymptote? And you can actually see that playing out here. 3 and 3, wouldn't those be the two areas? Like 3 would be the area for the piece on the left, and 3 would be the area for the piece on the right. You add them up, and you come up eventually. Count on your fingers, and you get to 6, right? So why on earth would in example 7, when we have something really honestly pretty similar, like if you just think about maybe this red area right here, isn't that red area conceptually and graphically very similar looking to what we did in example 4, this purple area right here? Yet in example 4, we got diverging, we got an infinite number or infinite concept. But in example 7, we got 6, which is very different, right, from diverging. So why, why would that be? That makes sense? Do you see why this is a little bit of a conundrum?
Yes.
Let me bring you back around to what I said a couple days ago. It's been a little while. We're going to start tightening this up a little bit and being a little more rigorous with it. But essentially it's this. The question of whether one of these integrals will diverge to infinity or converge to an actual real number has to do with how fast is the graph approaching the infinite discontinuity, or how fast is the graph approaching the horizontal asymptote. That's really the question. It's a question of degree. How quickly is it getting towards that, that important piece, whether it be a horizontal asymptote or vertical asymptote or whatever, or how slowly? And how do we decide, maybe is there a pattern between too fast or too slow, or not fast enough or not slow enough, whatever, that kind of thing? Maybe there's a pattern to it. And we're going to kind of be breaking that down a little bit today and a lot of second semester, okay? That's kind of the issue at hand. So I think what I want to do is I want to do at least one more example. I want to make sure we get to the final little piece of our puzzle here today. And I'll leave this up to you guys. This doesn't make a whole lot of difference to me. I'll give you the choice of either 8 or 9. I don't know. So there's not a 10, is there? No, I definitely want to do this stuff after 9.
Wow.
But 8 or 9, they're both kind of combinations of things. Any preferences?
8.
8, fair enough. So let's do 8. And if we have time later on this week or some other time we want to do number 9, we can always come back around to that. So number 8. Again, I want to give you an opportunity to try the bulk of this on your own. You're starting to get these skills in place. Why don't you give it a shot? We'll check your answer in a few minutes. Okay, guys, how many of you checked the graph on this one? Like maybe on your calculator you graphed 1 over x squared plus 5x plus 6. Hey guys, listen. I know Emma graphed it because I was watching. She graphed it and saw some stuff. Hey, did anybody else graph this?
No.
You really should have. Are there any vertical asymptotes on the graph?
I didn't. No. Well,
There are.
no, maybe.
I'll erase this here in a second. Yeah. So at -2, there's a vertical asymptote. And at -3, there's another one. And so let's see here. Does it looked like this, didn't it? Am I right, Emma? And then it did this, right? and then here. So that's what the graph of 1 over x squared plus 5x plus 6 looks like. This could have gotten really laboriously complicated if instead of the integral from -1 to infinity, what if it was the integral from -4
That'd be a
to
big
infinity?
issue.
Wouldn't that have just made this a way longer, more detail-oriented, lots and lots of labor kind of question?
Like it's still
What's it-
solvable, you just set more.
Yeah, you'd have to separate it into a bunch of chunks and eventually get there, but it would take like a couple of pages, I would be willing to bet. Right, it's going to take some serious space. The good news is, so some of you didn't even know what you avoided, right? You didn't have to worry about that stuff because we're accumulating from -1 towards infinity, and so we end up with this right here. So how long did it take you guys to figure out that this was a partial fraction decomp? See it pretty quick? Take a while? I hope you did see it. I think what it would look like is the limit as b approaches -1 from the right of the integral, not -1, what am I doing? Let's try this again. How about b approaches infinity, integral from -1 to b, and was it just straight up 1 over x plus 2 plus 1 over x plus 3? Minus. Okay. Which one came first, the plus 2? Okay, so it'd be 1 over x plus 2 minus 1 over x plus 3. If you do that partial fraction decomposition off to the side somewhere, I guess that makes sense. Okay, so then what is almost always involved in a partial fraction decomp? Natural logs. It's pretty much always going to be, for us at least, always going to be in there. So we'd go limit as b approaches infinity of natural log of x plus 2 minus natural log of x plus 3 evaluated from -1 to b. Okay, then you try out your FTC1. So that would be, again, limit as b heads towards infinity. Be ln of b plus 2 minus ln of b plus 3 minus, and then if you plug in a -1, it's going to be what? ln of 1 minus ln of 2. Do I have that right? Okay. How you doing? So far, so good? We're about to get some really curious results. So limit as b heads towards infinity. So let's see here. Let's clean this up just a little bit. So it'd be ln of b plus 2 minus ln of b plus 3. Are you guys okay with this just being plus natural log of 2?
Yeah.
Okay. Because ln of 1 is 0, right? Okay, so here's where this gets ultra interesting. As you try to apply your limit to this and this, in both cases, don't you get essentially ln of something huge? Ln of infinity, if you will. And we're, yeah, almost came out that way. So we were talking, hey guys, we were talking about, Liz asked a good question. How do I figure out this ln of infinity thing? And so I pointed her to a graph. This is the graph of natural log of x. And so as x, or in this case b, gets really large, ln of x just continues to increase the whole time, right? It's very slow, but it continues to increase. So would you guys agree with me that this would head towards infinity, and this would head towards infinity as well? So what on earth is infinity minus infinity? You want to say 0, don't you? You do. The problem is that works for real numbers, 10 minus 10, 20 minus 20, so on and so forth. Those are all 0, but infinity does not have to follow all those lovely real number properties. It doesn't. So here's what we got to do. This part is maybe a little bit past where I would expect you to go. Here's what you'd need to do. Did anybody think about condensing this log? If you're subtracting logs, how could you condense? Division. Yep. So it'd be natural log of b plus 2 over b plus 3 plus ln of 2 And here's where this gets super awesome. What do you get when you try to apply the limit now? So I'm not going to be a super stickler on the whole infinity over infinity conditions for L'Hopital's rule, but this is a L'Hopital's rule situation, isn't it?
My God.
The limit of the top is infinity. The limit of the bottom is
Is that
infinity.
why on the L'Hopital's thing, when it said infinity minus infinity, you said in the certain
Exactly.
cases it could be-
Exactly right. Yep. Okay. So then you can apply L'Hopital's rule here. Again, I'm not going to put the conditions up here because I'm going to go fairly rapidly through this. But what's the derivative of the top and the derivative of the bottom?
1.
1. That's right. So limit as b approaches infinity of natural log of 1 plus ln of 2. What's the natural log of 1?
0.
And at this point, there's nothing for the limit as b approaches infinity to even apply to.
So this is yellow.
So the answer is 0 plus ln of 2, which of course is natural log of 2. So this does not diverge, it converges to ln of 2.
You have to keep going.
Who would have thought?
So, don't,
The mistake you made was thinking that infinity minus infinity was 0.
but I said it.
That's what.
Or diverges for that
Yeah,
matter.
yeah.
Infinity minus infinity is basically a nonsense, indeterminate answer.
But if you have something, even though that it goes on forever, it's something.
In the time that it took you to think about it, the first one got bigger than the other one. And when you rethought it, the second one got bigger than the first one.
It's the exact same concept. This concept is.
That's the thing, it's a concept. And who says that they're going at the same
Why
rate?
is the exact same concept.
That's the thing you
Why
don't
is it
know.
not the same concept?
It's simply not. Because that property only applies to real numbers, infinity's not. Not a real number. It's hard to wrap your mind around, and we'll spend most of the rest of the year trying to wrap our minds around that. We really will. So don't stress if you don't like totally have that idea rock solid right now. We'll keep at it. It is interesting. Agreed. So guys, I've been hinting about this a little bit. I wanted to formalize this somewhat. So at least 2 different times, maybe 3 times, I've brought up the idea of why does this integral diverge towards infinity and why does that one converge to a real number? And so I want to start to shape this up a little bit for you. There's a lot more things to consider off in the future, but this is one of them. So some general thoughts on this as far as divergence and convergence using what we call the p-test. This is where everybody snickers, or at least some people snicker, and they're like, p-test, ha ha ha, I get it. So if we can get that out of the way, that'd be lovely. So the letter P in this one stands for power. Okay? That's why they use the letter P. Call it the power test if you want, but everybody calls it the p-test, or whatever. So if you think about it, all the ones that have been a little bit curious, they've been things like this. The integral from 1 to infinity of 1 over x. Another one we did was the integral from 1 to infinity of 1 over x squared dx. We just did essentially, we did some a few minutes ago where it was like integral from 3 to 4 of 1 over x minus 3 to the 2/3, I think it was. Stuff like that. So it has to do, the pattern we're looking for has to do with all these powers, like the 2, the 2/3, of course the implied 1 right there. What does that mean for a diverging answer versus a converging answer? The p-test kind of starts to develop this a little bit for us. So here it is. If you have the integral from 1 to infinity, and this is very specific, it's not 1 or some other number, it's specifically 1 to infinity of 1 over x to the p, where p is some exponent like 1/3 or 2/5 or 9 or 2 or whatever. Then, if p is bigger than 1, so 1.1, 2, 3, 5, 9.6, 27, 36, whatever, then that integral specifically converges to this number right here, 1 over p minus 1. Interesting, right? But if p is smaller than or equal to 1, then we're heading towards infinity. Divergence, right? So again, why is this? There are some deeper answers that you wouldn't look at until you got to a real analysis course. There are some less deep answers that we will look at here for why that is. For the moment, maybe remember this and use this to your advantage. Okay, so example 10. What are all the values of p for which the integral from 1 to infinity of 1 over x to the 2p. So it's no longer just a exponent of p, it's 2p. What values of p would that integral converge? And that's obviously a multiple choice. So that would give you a little example here of what you might be asked. Or the p-test would make this a little bit easier. So any thoughts? What could I do? Any answers, thoughts, considerations? C? Okay. Okay, there you go. Yeah, I like that. So if we think to ourselves, hey, the overall exponent has to be bigger than 1 to get a converging answer, we'd say, well, the exponent is 2p, and we need that to be bigger than 1. Makes a lot of sense. And then as you suggested, you solve. So p would have to be bigger than 1/2. So agreed. The answer would have to be C. Okay? You will use this p-test extensively this year. This is just a little taste of it right here. Okay. Yeah, Jaden, go ahead.
So is this true only if the infinity is the lower limit of integration and 1 is the lower limit? Or is the constant the lower limit?
So yeah, we can extend this a little bit. So if you had the integral from like 4 to infinity of 1 over x to the 5th, let's say, clearly that exponent of 5 is bigger than 1. So what we could say about that one is that integral definitely converges. We just couldn't say that it converges to that nice convenient 1 over p minus 1 number. Does that make sense? So we could say, hey, yeah, sorry, I wrote it right in the wrong spot there. The p value is 5, which is bigger than 1. So I'd say something like this. P is bigger than 5, or sorry, p is equal to 5, which is bigger than 1. Therefore, the integral converges. I wouldn't be able to say exactly what it converged to, but I would say, yeah, it definitely converges. Okay, I got one more thing to say, but maybe I'll come back to it at the end. It's not terribly important right now. Any other questions, thoughts?
Wait, so could you say that because it's saying that the integral from 1 to infinity, if it's in that form, and say that p was 5 like we had, then can you just say that that integral value is equal to 1 over 4?
No. So that little formula of 1 over p minus 1
That's just
only specifically works if the lower limit is 1.
So if the lower limit is 4, it would be limit of 3 minus 4.
No,
Oh, okay.
it would be something else entirely, which frankly I don't know what it would
But
be.
if it is in that whole form, you could say that it equals 1/4.
Which is astonishing. Yeah, truly an astonishing result. Yeah. Get a doctorate and you tell us. I kid you not.
So you can't.
Really?
Yeah. No, like the people that develop and prove these things, like this was, I mean, obviously this particular thing has been around for a long, long time, but proving that kind of thing is usually a doctoral thesis that would take you years to prove and defend and have all these other mathematicians be like, I think that's wrong. And you're like, well, I think it's right, and here's why. And you have this math fight, and you leave with your tail tucked between your legs. You're like, I was wrong. You go back and try to fix it or whatever, or reprove or redo whatever. That's where these things come from. So it's not this trivial, oh, that's the answer. People will shoot you down or they'll try.
Well, they have to.
And eventually you prove them wrong and yourself right. And they're like, all right, you can be the doctorate of math. Yay.
Wow.
So yeah, it's not a trivial process.
So
Yeah.
you can't, like, can you or can you not apply the 1 over p minus 1 for that because it's 4 and not 1?
What you just said.
You can't?
You can't.
You can say it converges, but you don't know where.
That's right.
So is that rule because
Let me just say this. We
is that
won't
totally different then?
we won't use this relationship very often at all.
Okay.
But we will use the, hey, p is bigger than 1, therefore that integral converges thing. We'll use that a lot. For sure. If in doubt, just go ahead and do the improper integral, and you'll find out yourself. It's okay. All right, so the last thing here is, again, just kind of a taste of future stuff. And this is comparison. And this goes back to this. We'll just take our last couple of minutes to talk about this, and we'll see how far we get. But do you remember, like, the basic concept I mentioned is that the reason why this integral converged to some real number and this integral over here did not converge to some real number, like it was infinity or something, has to do with the rate of approach towards either a horizontal asymptote or an infinite discontinuity. It's like how fast or how slow is it moving towards that, right? So this comparison test kind of piggybacks off that a little bit. So let me just give you an example of what you could do. So an example where you could use comparison to show convergence. Let's say you had this right here, the first example, and to be perfectly honest with you, I think you understand this. If I actually tried to evaluate that integral, I would run into some serious issues, right? 1 over x cubed plus 1. Is it an arctan? Nope. Is it a natural log? Nope. You'd run out of options pretty fast. Is it a nice partial fraction decomp? I don't know if it is or isn't, but it's definitely not a nice one if it is. And so you might be convinced, well, you know what? Maybe I shouldn't be so concerned about what this is and just be concerned about converging or diverging. So check this out. I don't expect you to be an expert at this right now. So I'm just like giving you a taste of some stuff to come. What if I considered something that I do know a lot about? For instance, what if I said, I know a lot about, and I would bet, as sharp as you guys are, you know this one pretty quick. If I looked at this and thought, hey, what about this other integral, the integral from 1 to infinity of 1 over x cubed dx? Would you guys say that, based on what we just talked about, would you say that that integral converges or diverges? Converges because why?
3
P is 3, which is greater than 1. Sure. So converges because P equals 3, which is bigger than 1. So in other words, 1 over x cubed approaches that horizontal asymptote fast enough to where you'd get a real number answer if you figured out what the actual integral would add up to be. That make sense? So then how would you say 1 over x cubed plus 1 relates with 1 over x cubed on the graph? Like if I thought about the graph of this and I thought about the graph of that, how would they relate?
Is it just a little bit further to the right?
Think about verticality. Don't think you guys are all mentioning like left to right, shifted right, this,
It's
shifted.
the
go
same.
up one? Shift
No,
up.
it's the same, isn't it a horizontal?
Does it go up one?
What?
Nobody's ever answered this with shifting before. That's really interesting to me. Think about the denominator.
Oh.
Think about the denominators. Which denominator will be smaller?
X cubed plus
Or
1.
it's denominator.
No. This
X cubed plus
this denominator right here that I'm highlighting in red, won't this one always be a little bit bigger than the other denominator? It'll always be bigger by how much? 1. So no matter what the x is, this denominator will always be 1 bigger than the other denominator. And if the denominator is bigger, the overall value of the number is smaller. So here's the idea. If 1 over x cubed approaches fast enough to converge, and x cubed plus 1 is always bigger than x cubed, which would make 1 over x cubed plus 1 always a little bit smaller, wouldn't it be getting there even faster? So in other words, if we thought about a graph, I would say, yeah, converges plus 1. Here's 1 over x cubed. Wouldn't 1 over x cubed plus 1 be, for the part we care about, wouldn't it be down here somewhere? From 1 over? It would be below it, wouldn't it? So if the purple graph approaches fast enough, wouldn't the red graph have to approach fast enough as well? From 1 over? So what we could do is say something like this. 1 over x cubed plus 1 is less than or equal to 1 over x cubed on the interval that we care about. Therefore, the original integral also has to converge.
So you don't have to say where, you're just determining if it does.
Yeah, if it's just a question of diverge or converge, we can use something like
Could
this.
you find out where it
Like to how much it converges to?
Yeah.
Again, that's actually either some crazy formula or doctorate question, and not as easy as we would hope. So mostly in our course, with a few exceptions, we'll be concerning ourselves with, does it converge, does it diverge, and why? So again, like this has been a little bit of a taste of some future event kind of things. If you get a hold of it and you're like, hey, I think I could use that, and you end up using it, it's still good math, it's fine, but nobody's expecting you to be like this total master of this right now. Just a little preview. We'll do that on Wednesday. You can see your grades, right? You saw your grade? Okay, cool. All right, have a wonderful day. See you guys.